Hi everyone, and welcome to the final video in this series looking at some past exam questions on rate concentration graphs and also the rate determining step. This question doesn't involve a rate concentration graph at all, but there is a part about the rate determining step which we'll get to later on. I wanted to go through this example question with you because it's slightly more challenging than some of the ones that we've looked at before. Okay, it looks very similar. Hopefully you can recognize this type of question, right? As soon as you get a table like this with various experiments and concentrations in it, you should be thinking, I know what I'm going to have to do here. This is going to be orders of reaction, work out the rate constant, this kind of thing. And if we have a look, that's exactly what it says. Here's our reaction. They investigated the rate by carrying out some experiments, okay? But it's a bit strange here, it's saying the rate equation is this, okay? And they're asking us to show that the results support the rate equation. So because this question is a little bit more challenging, and we'll see why in a minute, they've already given you the answer. So you just need to prove that that is correct. Okay, so at least when you get through the question, you'll know if you've got it right. You know, if you get through it and you end up working out that the H2O2 is second order, you've done something wrong, okay, because you know what the answer is supposed to be. Okay. Then we need to calculate the rate constant and work out the units, and they are specifying significant figures and etc. So we need to be careful when we get to that point. Okay, and as always, we need to make it clear how the experimental results link to the orders of reaction. So if we have a look at this table then, remember what we're always trying to do is to find experiments where the concentration of only one thing has changed. Okay, so then we can see what effect it's had on the rate. So if we have a look at experiments 1 and 2, the concentration of the hydrogen peroxide has doubled. The I minus has stayed the same and the H plus has stayed the same. Okay, so whatever change has happened to the rate is only due to the hydrogen peroxide. And then what has happened to the rate, again, this might not be obvious to see because we've got a change in the power of 10. So let's just divide this on the calculator. You might be able to see this just by looking at it. But it's 1.14 times 10 to the minus 5 divided by 5.7 times 10 to the minus 6. And we can see that that's times by 2. Okay. So far this is fairly straightforward, right? We're going to say from experiment 1 and 2, the concentration of H2O2 has been times by 2, and the rate has also been times by 2. Therefore, the order with respect to the H2O2 is first order. Okay, lovely. Right, then we want to try and do the same thing again. Let's try and find two experiments where only one concentration has changed. So looking here in the table, if we look at experiments 2 and 3, then the H2O2 has stayed the same, the I minus has stayed the same, and the H plus has changed. Okay, so again, we've got only one concentration changing, which is what we're looking for. So here, the concentration of H plus has times by 2. And what's happened to the rate between these two experiments? Well, you can see that it's stayed the same. Right, so we say times by 1. Okay. So we can then make a conclusion here from experiments 2 and 3. The concentration of H plus has been times by 2, and the rate has been times by 1, or it's unchanged. So what does that mean then? Well, if we've changed the concentration and it's had no effect on the rate, it means it must be zero order. Okay. And just as sort of an aside here, now that we've started talking about the rate determining step in some of these other videos, we can now actually start to understand how something can be zero order. Okay, you think, because it kind of doesn't make sense. Well, why does it's involved in the reaction, but changing its concentration doesn't affect the rate? That's a bit strange, because it's not involved in the rate determining step. Okay, it'll be involved in one of the faster steps. So therefore, that's why it's zero order. It's not having an effect. It's still required. You can't do the reaction without it, but as long as you've got some of it, having more of it doesn't really make any change to the rate because it's not involved in the rate determining step. So the order with respect to the H plus is zero order. Right, finally then we need to look at the I minus. So we want to find some experiments where the concentration of the I minus has changed, but the other two have stayed the same. So if we have a look in the table here, the I minus is the same all the way down until experiment 4. So we're going to have to use experiment 4, but we've got a bit of a problem. Okay, we've always got more than one thing changing at a time. I think the easiest thing to do here is to look at experiment, it doesn't actually matter, let's look at experiments 2 and 4. Okay, if we look at experiment 2 and 4, there are other combinations that you can choose here, but this is the one I'm going to choose. I'll explain why. So we need the concentration of I minus to have changed, right? That's the one we're interested in. So from here to here, the concentration has doubled. Okay. Unfortunately, there is no combination where that's the only change. So the H2O2 has also changed between those two experiments. That has been doubled. But at least the H plus hasn't changed. So that's one thing we don't need to worry about. Okay, that's one reason why I've chosen experiments 2 and 4. So at least they haven't all changed. Okay, that hasn't changed at all. So actually we don't need to worry about that. And what has happened to the rate between experiment 2 and 4? Okay. We've gone from 1.14 to 4.56. So hopefully you can see this has been multiplied by 4. Okay. So let's just write this down and we'll think about what's going on later. So if we say, right, from experiments 2 and 4, what has actually happened? The concentration of H2O2 has times by 2. And the concentration of I minus has times by 2. And the rate has times by 4. So we're kind of stuck here because we don't know what effect both of these things have affected the rate, but how much? Well, actually, we do know that, don't we? Because we already know what effect the H2O2 is having. Okay, we've already worked out that H2O2 is first order. Okay, so since we know that H2O2 is first order, if the concentration of H2O2 has been times by 2, okay, we would expect the rate to have been times by 2. So we would have already expected the rate to have been multiplied by 2. But the rate has actually been multiplied by 4. So the difference between what we would have expected and what has actually happened, that must be because the I minus has changed as well. Okay. So the concentration of I minus being multiplied by 2 has caused the rate to times by 4 instead of times by 2. Okay. We'd expect it to be times by 2 because of the H2O2, but it's actually times by 4. Okay. So therefore, the rate is double what we would have expected. We'd have expected it to be times by 2, but it's actually times by 4. So it's twice as big as what we would have expected, and that's because the I minus has doubled. Okay. So therefore, the order with respect to the I minus is first order. Okay, because the I minus has doubled, and the effect that has had is to cause the rate to be times 4 instead of times by 2. So in other words, it's doubled there. Okay. Then we need to go through the procedure that we normally do, calculate the rate constant, and then work out the value and work out the right number of significant figures. Okay. Before we do that though, let's just check. Thankfully, they've already given us the answer, haven't we? So what have we said? We have said H2O2 is first order. We've said that I minus is first order. And we've said that the H plus is 0 order. Okay, so we've got it right. Okay, we can actually check before we start doing everything else. It does match up with what they've already said. Okay, let's rearrange our equation then. I'm running out of space here, so I'll do this up here. So K is going to be equal to the rate over the H2O2 concentration and the I minus concentration. Okay, so then I will calculate that at the bottom here. So K is going to be equal to, again, it doesn't matter which experiment I choose the values from, we'll just choose experiment 1, but it should give us the same values anyway. oh, get it right, 5.70 times 10 to the minus 6, divided by, make sure you pick the right concentrations here. It's very easy to get the wrong ones. So we want 0.001, and the concentration of I minus we want, which is 0.2. I'm going to ignore this one because it's zero order. So therefore, if we calculate this, 5.7 times 10 to the, oh, what am I typing? 5.7 times 10 to the minus 6, divided by 0.001 times 0.2. I've got the right number of zeros, yes, okay. And we get 0.0285, but it did say something up here, didn't it? Give your answer to two significant figures in standard form. Okay, so this then is going to be 2.9, isn't it? Times 10 to the minus 2. Okay, and then we do need to work out the units. So if we go back up here, we can say that it's going to be moles per decimeter cubed per second over, you can see I'm going to shortcut this because I'm running out of space, moles per decimeter cubed squared. We can cancel out one set of moles per decimeter cubed, okay, and so we're going to end up with units of seconds to the minus 1 over moles per decimeter cubed. So it will end up being decimeters to the positive 3 moles to the minus 1 seconds to the minus 1. Okay. So I just wanted to show you that example where if you're stuck and you can't find two experiments where only one concentration is changing, it doesn't mean that the question is impossible. If you work out the ones that you can do first, you can then use that knowledge you've already got to be able to work out the trickier ones later. Okay. This question then continues, and it then asks us, the student concluded that the H+ ions act as a catalyst. Okay. Explain why the student's conclusion is not correct. Okay, well, what does it mean if it's a catalyst? A catalyst is something that speeds up the reaction by providing an alternative pathway, lowering the activation energy and so on. But a catalyst doesn't get used up. Okay, if we look at what it's saying, we've got H+ actually as a reactant in the equation. Okay, it's actually reacting. Okay, a catalyst would not be written as part of the equation. Okay. So the H+ ions are one of the reactants. Okay, they are used up during the reaction. So it is not correct to say that H+ ions act as a catalyst. And here we have the section about the rate determining step. It's saying a 4-step mechanism. So again, this is slightly more challenging than the questions we've looked at before. A 4-step mechanism has been proposed for this reaction. The rate determining step is the first step, right? That's actually going to be important. What is meant by the term rate determining step? Well, again, it's one of those, it's exactly what it sounds like, but how do I write that? You can't write, it's the step that determines the rate. You're not going to get a mark for that. The rate determining step is the slowest step, is what it's looking for here. Okay, and that's why it determines the rate. It's the slowest part. And then they're asking us to predict this mechanism. And we've got 4 steps to do here. Thankfully, they've done one of them for us. Which otherwise, we wouldn't be able to do the question. But you might be looking at this thinking, where do we even start? Okay. Well, we start with the rate determining step, okay, as we've done in any of the other rate determining step questions. Okay. They've told us that the rate determining step is the first step. Okay. Remember that there is a link between the rate determining step and the rate equation, isn't there? Whatever's in the rate equation is in the rate determining step. Okay. So if we go back to our rate equation that we have here, in the rate equation we've got H2O2 being first order and I minus being first order. So therefore our rate determining step should have 1 molecule of H2O2 and 1 I minus ion. Okay, so that's where we're going to start. We're going to start here with H2O2 and 1 I minus ion. I'm just going to write the overall equation here at the bottom, because it's over on the other page, just so you can see it. So the overall equation is supposed to be H2O2 and 2I minus and 2H plus, making I2 and 2H2O. That's the overall equation that we're looking for. So, like we've seen on the other videos then, if these are the reactants, what are we going to make? Well, we're going to try to make the right products here. There is no way that we can make I2 out of this stuff, because we've only got one iodine. We could make H2O though, couldn't we? Okay, we just take an oxygen off. So let's make H2O. We're then left with an I minus ion and one oxygen atom. So let's just shove those together, okay, and call it IO minus. Okay. You might be looking at that thinking, what on earth is that? It actually doesn't matter, because what are we going to do with this? This is not supposed to be one of the products, so straight away we're going to use this up and get rid of it. Okay, and because it's an intermediate, because it's going to get used up and used up quickly, because remember the rate determining step is the slow step, okay, which therefore suggests that all of these steps must be fast. Okay, it's okay to make something that perhaps you don't recognize here, because you're making excuses for it straight away by saying, yeah, I know this is a bit weird, but it's not going to be around for long. We're going to get rid of it pretty much straight away. Okay, it's going to be reactive and it's going to be gone. Okay. Then we need to look, okay, what are we going to do with this? Right, again, we're going to compare what we've already written to what the actual equation is supposed to be. We're supposed to have H2O2, right? We've done that. We're supposed to have two I minuses, we've only got one, but the other one is already here, right? So those have all been accounted for. So therefore, the only thing that this can react with is H plus ions. Okay, and the only question then is, are we going to use both of them, or are we just going to use one of them? Okay, we're at least going to use one, aren't we? And therefore, what's it going to make? Well, where are we going with step 3? You can see that step 3 starts with HIO. Well, where has this come from? Okay, this has come out of nowhere. It hasn't come out of nowhere, it's come out of this reaction. Okay, so therefore we do actually only want to use one of these H pluses so that these two can react together and make this, so that it's there for step 3. Okay, so we're going to make our HIO here for our step 3. Therefore, the only thing we've got left from the reactant is one H plus ion, so that must be going in step 4. So hopefully you can see then from our reactants we've used up the H2O2, we've used the two I minuses, and we've used the two H pluses, so they're all done. Okay. Right, what about the products? We're supposed to make I2, that's coming from step 3, so that's done. And we're supposed to make 2H2O. Well, I've got one here, and that's it. So I must be making another H2O in this final step. Okay. And then I've got everything. So now what? Well, now I need to do some tidying up, right, with all these intermediates and things. Okay, we already talked about the IO minus, going, it's a bit dodgy, but we can tidy it up and get rid of it. We made this HIO, which again, you're perhaps not familiar with, but we've got rid of that. Okay, so the only thing we've got left here is we ended up making an OH minus ion here. And you should find, again, it's always nice, these questions, you know if you've got them right, because you go, oh no, what am I going to do with this? Oh look, it works out perfectly to give me what I want. Okay, you should find that it works out nicely. Just do a check here then and make sure that all of the stuff cancels out that is supposed to cancel out. We said we're cancelling out this IO minus. Again, you don't need to do this. This is just proving to yourself that you've got it right. It's not required for the actual marks. The HIO cancels out and the OH minus cancels out. And then hopefully we should be left with this equation. Let's just have a look. H2O2 plus I minus plus the other I minus and plus 2 H pluses gives me I2, that's the product of step 3, and my 2H2O. So there we go. Okay, it is quite challenging, this type of thing, but hopefully you can see it does follow a logic. You can kind of work out where to go next, hopefully, but that might be something that you need to practice.